Very good. Good morning. So today we will talk about the kind of topic that makes me like this field of machine learning, because it's a phenomenon that was unknown a couple of years ago. The phenomenon is called double descent. Who has heard about it? Okay, and who has learned how to interpret it or how it comes about? Okay, very good. And when this type of new phenomenon appears, then three things happen in order. First, there's general disbelief, this can't be true. And then when it is reproduced, then there are two factions of people coming out, one saying, yeah, we knew all along. There's a paper I wrote a paper in the 70s, before I was born, which, already claimed that. And then the other faction tries to rationalize and explain. And if we say that in machine learning, there are also experimentalists and theoreticians, so far, I think one has to say that, overall, it's been 1-0 in favor of the experimentalists. So if we look back at the last 20 years of machine learning, people have tried out stuff. They moved fast and broke things. And then afterwards, the community has struggled to try and understand and explain it. And I have to say, for example, myself, I eschewed deep learning for a long time because I like to understand the things that I do. And I was working on convex optimization problems or combinatorial optimization problems where you can really understand in detail what you're doing. But we have to say that this field of deep learning really, took the day. And now this phenomenon of double descent, today we will, it can be discussed at least partly even in the context of linear regression. So we are still talking linear regression today, but we're moving further and further from what you've seen in high school days. And last time we were discussing regularized regression. We were talking about the ridge, we were talking about the lasso, that can help us stabilize estimates. We had in either case this parameter lambda, which told us how strongly we want to regularize. And we left with the question, or I did not answer the question, how do we pick a good lambda? And so today we will start by discussing how to pick a good lambda. And to save ourselves lots of writing and time, today I put this in this public OneNote document. I can show the link again later. So we have two cases. Either we have lots of training data or we have little training data. Usually we have too little. But here the discussion starts, what if we have lots of training data? Maybe I can find a huge pointing device without a broom attached. No. All right, now just use the mouse. So if we have lots of training data, then one possibility is to partition it. You take some percentage, maybe 80%, and call this your train data. And then you take some fraction and call it your validation set. You take some fraction and call it your test set. Confusingly, there are two conventions. Other people call this train test validation instead of train validation test. There is no right or no wrong. It's just a matter of how many people follow one convention or the other. And then on your training set, you can then simply run lots of models. So in our case, in ridge regression, we have just a single hyperparameter. So grid search is easy. Well, and actually, when I say grid search, that suggests that when I have multiple parameters, that it might be a good idea to use a Cartesian grid. So let's say we vary the first parameter and we vary the second parameter and we make a grid of such experiments. And in fact, that's a bad experimental design. So it's much better to sample randomly from the hypercube for reasons that we can discuss another time. All right, so you train multiple models and then you try out all these models on your validation set. You pick the parameters that work best and then evaluate on the test set. And the idea is to use this test set only once. And in practice, there is a huge temptation to break this rule. And you know, you have your favorite parameter set. It does terribly on the test set. Well, then maybe you take your second best parameter set and does a lot better. And then you go and run with your second best parameter set. But you know, there you've already started training on your test set. And you know, as long as it's a single parameter, it's not so bad. But once you have many parameters, and once you start doing this many times over, things get really fishy. Yeah? And then with your favorite hyperparameters, you can then train your final model on the union of train and validation and test. And this is the one that you're going to deploy. Okay, frequent errors. Train and test set in reality often are not as independent as they should be. So, for example, CIFAR 10 is a database of images and class labels. And for example, there are images of cars, or you know, some white sedan in there. And our colleague Dimitri Kobak, whom I mentioned last time, he then did a UMAP embedding of this data set and found a really tight cluster of images. And these were identical, like 20 identical pictures of the same car from the same perspective. Nobody had known before. Yeah? So there were replicates in this data set. And if you now partition your data set randomly into train and test, well, then you're going to have these replicates in both. And you know, as long as it's only 20 cars out of 1,000, it doesn't matter so much. But you see the problem in principle. Another typical error is that the second point here, that people use, let's say, the first 80% for training and the next 10% for validation and the final 10% for test. And this is really bad because many data sets have some structure, some order in there. So we had this discussion just last week in my own lab. Yeah? So we're working on a big data set. It's called QM9. It has 130,000 molecules. And a student working on the data, he took the first 2,000 samples. But it so happens that the way this collection has been generated, it's been generated artificially, and it started with the tiniest molecules and then grew them and grew them. So the first 2,000 were also the smallest 2,000, and there was some additional structure in there. So it's really important to make this partition random. And then, as I said, you know, not use the test set over and over. This is, by the way, you know, oftentimes there are challenges out there like Kaggle, where, for example, a pharmaceutical company puts out a machine learning problem and they say the winner gets $10,000. And then in the early days of this kind of competition, then people started submitting not one solution, but they were submitting, let's say, okay, basically, in the extreme case, you can just submit, if you have 10,000 test samples, you can keep submitting solutions and keep changing each, one label at a time of the submission that you give, and see, does it get better or worse? Yeah, so you do directly gradient descent on the test set, and this is why these kind of competitions, why they now have these rules that you can submit, maybe one model a day or so, to reduce that problem a little bit. Okay, now all of the above was in the hypothetical case that you have lots of training data. Yeah, so 100,000, 130,000 molecules is not so bad. In most cases, or in many cases, people come with you with maybe 100 labeled images or objects. And they might have many more unlabeled. This is why this field of self-supervised learning is so important. But generating labels is often expensive, so somebody needs to sit down, or you need an alternative technique that is more expensive to generate those labels. And so label data is often scarce. And so if you are not rich in training data, we now come to this second case, then cross-validation is for you. So you partition your data randomly into k equally sized groups or folds, and then you do the following. You could take so let's say we have, you have partitioned your data into 10 folds, and then you repeatedly take 9 out of the 10 to generate new training sets. And on each of these training sets, you train a model, and then you test it on that part of the data that was not used in this particular training procedure. You do this for multiple models, you see which hyperparameter works best, and then you can estimate on this average over your k artificial test sets, how well did your regression method or your classifier do, and also how big was the deviation from one of these small test sets to the other. And then using your preferred hyperparameters, you can do one of two things. You can either then train your model on all of the data and deploy, or you can use the bunch of models that you have generated, and then you have an ensemble, which is actually quite nice if you can afford the compute, because that gives you, on new samples, a little bit of an uncertainty estimate. Yeah, so if you get if you now really run it out in the wild, you get a new sample, you make predictions. If the predictions agree pretty much, you are happy. But if the 10 models make widely different predictions, then you may start to wonder, if this new sample, is it an outlier or does it lie too far from what you have been training on? So, good thing about cross-validation, it works with small data sets, and as I've just said, it gives you an ensemble and a sort, I don't want to call it error bar in the strict statistical sense, but it gives you some form of uncertainty estimate. Yeah. And then there's some bias in there. Here I'm writing the accuracy estimate can be too optimistic. When you've tried out too many hyperparameters, it can also be a little bit too pessimistic because you only use k-1 over k parts of the data. So these accuracy estimates are not going to be fully reliable, but this is a really useful method in practice. Okay, so much about cross-validation. Do you have any questions about that? Yeah. Yeah, so I'm repeating here for the microphone. The comment was that it's computationally intensive. And now for some methods, for linear methods, you could use rank 1 updates to take your first model and then update it to the second training set rather than retrain. In practice, however, this is not done. Yeah? So in practice, you would really train independently, and the fact that you use different initializations would be seen as a feature rather than a bug, yeah? Because it lets you maybe explore a little bit more of the model space. And I mean, if we're discussing the training of large language models, then we're discussing millions of dollars, and it starts to become unaffordable. But for the kind of architectures that people normally deal with, it's doable. More questions or comments? All right. So this much for cross-validation. And now I would like to talk about the bias-variance decomposition leading up eventually to this phenomenon of double descent. I want to mention it because this has guided, this has been the guiding star of the field, let's say for its first 50 years, and yeah, is called, okay, not called into question, you know, what I'm going to write is true, but it turns out to be more subtle, as we will see after this part. Yeah? So I will talk about it in the context of regression. Yeah? So we have some true underlying function. We have some noise, and we assume that this noise has a zero mean. For this discussion here, I will also assume that its variance is known. And then we have some estimator y hat. Yeah? And now we can look at the expected mean squared error. So we have some prediction y hat. And we have this. Strictly speaking, I should now also write minus epsilon here, but the sign doesn't matter anyway. I will just put a plus here. Okay, we take the square, and this is the expectation. And we want to first separate out the irreducible error. So just going to multiply this out. It's plus now I'm taking the mixed term here, so we have twice the expectation of this y hat minus f of x times epsilon. And this all right, and this expectation here, I am taking with respect to epsilon. Let me see. So I'm trying to figure out why this part here. Okay, let me see. Ah, interesting. So I want to see why this part here cancels, and y hat is my estimator, and I'm trying to decide if or not this depends on epsilon. And I tend to think that it does. And this is why I cannot just pull it out of the expectation value. Interesting. Okay, I'm confused. So, let's look at this part here. We had the expectation. So the f of x is deterministic. Yeah, so I can pull it out. I can say this is f of x times the expectation of epsilon, and this part was assumed to be 0. But there is also this part of the expectation of y hat of x times epsilon. And here I am not sure why I can argue that y hat does not depend on epsilon. Because my estimator y hat, well, I estimated it from my observations, and in these observations there was an epsilon in there. Yeah? So this here supposedly is 0, but I cannot argue right now why it should be 0. Okay, it was clear to me yesterday when I looked at it, and it's no longer clear to me now. Okay, I'll come back to this. This part here is sigma squared, and this part would be called the irreducible error. And the first term, that's the prediction error. All right. Okay, now, for the moment, I claim this is 0, even though I cannot give a convincing argument. I'll give that argument next time, yeah? And for now, I look at the prediction error. All right, this prediction error, so we have the y hat minus f of x. And now a small trick is used, namely to subtract and add its expectation value. All right, now I've subtracted and added the same thing, so this is 0. So the left and the right-hand side are the same. And now we call this the first term and this the second term, and we can square them and write their mixed term also. So this would be y hat of x minus the expectation of our predictor squared plus the second term squared it should be minus, thank you. All right, and here, now this time, here is a constant. Yeah, I've taken the expectation of it, that's a constant. This is also deterministic. So this nested expectation here I can remove. I can remove this expectation in this square bracket. But I still have the mixed term. So it is expectation of y hat x minus good. And now if we look at the first term here, this is a constant, so I can take it out of the expectation. So what this part here would read, it's the expectation of y hat of x minus the expectation of y hat of x, and that's 0. Yeah, and so this whole last term here vanishes. And I'm left with these two. And this one here would be the variance of the estimator. So it's expected squared deviation from its mean. And this here is called the squared bias. So squared, because we have this 2 here, squared bias. So how much the bias is, how much the expected estimator deviates from the true function. All right, and now I had some time to think about this issue up here. I think the argument I can make is the following, that the expectation that I take here is with respect to two quantities. One is which samples enter the training set. So I'm writing D here for data set. And the second source of randomness is the noise itself. And here in this part, I would take the expectation with respect to the data set. And here I would take the expectation with respect to epsilon only. And if I do that, then this part does not depend on epsilon, and I can pull it out. And then I would also claim that, all right, it's something times the expectation of epsilon, which is 0, and hence the whole thing is 0. Okay. All right, so this is the bias. So the whole thing was called Bias-Variance Decomposition, and it was called that because we have here the bias and the variance, and the squared bias and the variance together make up the prediction error, and the prediction error and the irreducible error together make up the expected mean squared error. Now let me draw some pictures to complement this. So let's say we have this regression problem, and we have some observations. I'm claiming that these observations were generated from some true underlying function f of x. And now we have our models. And in this case, I'm using linear regression. And now depending on which sample set I draw from the underlying distribution, I might get this linear regression, or if I sample new training data, I will not get perfectly the same line. Yes, I will get here many linear regression models. Now, from these regression models, I can take their expectation. So this bold red line here is the expectation of my models that I'm learning. And now we have two kinds of quantities here. We have this deviation, how should I draw that? Let's say this deviation here of the individual models from the expected model, or from the expectation. That would be the variance. And here I have this systematic deviation of the true underlying function from the expectations over the models that I've learned. Yeah, and this part here, let me call this the systematic error. If we take that squared and its expectation, that would be the squared bias. Okay, now this kind of decomposition has been used to motivate the following picture, which was generally considered valid until the first cracks appeared, or the first cracks were more widely noticed in 2018. On this axis here, I'm writing model capacity or model flexibility. And now we have the classical regime, which makes the following argument. Up here is some error, and I can need to think about my colors. Classical, modern, training and test. So let's say my training error goes down until it eventually reaches 0. This would be the training error. And what we usually observe with the test error is that it is usually a bit higher than the train error, but it drops as we make our model more expressive, until eventually we start overfitting, and this increases again. Yeah? So this would be the test error. And this is the plot that all the textbooks, I would say even the textbooks that you can read today have, because what we will discuss after the break is not yet in the standard textbooks really. And so in this classical regime, here our test error is too high because our model is too stiff. Like here, in the example I gave, we see some clear nonlinear trend in the data, but we fitted it with straight lines nonetheless. Yeah, so here I was dominated by bias. And so here on the left-hand side, I have underfit. And then I have some optimum. And on the other side, I have overfit. And this underfit would be dominated by bias. Okay. I'm sorry, this is getting small now for people sitting in the back. So I'm writing underfit, too much bias. And here to the right side of this optimum, I'm writing overfit, where I have too much variance. So because you can imagine that if I don't use here a linear regression, but if I use some, let's say polynomial with many degrees of freedom, my linear regression models are reasonably similar, but if I use more flexible models, they will differ from each other a lot more. All right, too much bias, too much variance. And here is the optimum, which we would identify using, for example, cross-validation, discussed earlier this morning. Okay, so much for the classical picture. And now the surprising finding. And I'm going to call this the modern regime. So how did this come about? Even before this particular paper was written, people were training models with way too many parameters. Yeah, so normally when we talk linear regression, we would say that you should not use, okay, let's say, let's be specific. X and Y, if I have two observations, then you would say normally, okay, a model with two parameters, slope and intercept, is the most that I can fit here. I cannot reasonably fit a model with more free parameters than observations. Everybody would nod and agree. Now, in the 2010s, people were starting to train neural networks on, for example, image classification problems. And then there were, maybe 1,000 images, or maybe there were 1 million images, but the neural networks trained had 10 times more free parameters. Now you can start making arguments, yeah, but an image has many pixels and they're not fully independent and I don't know what. Or you could maybe say that in image classification, we have many labels or many categories of what can be in an image. And maybe this is like having replicate data sets where each data set just has yes or no classifications. But the fact remains that the most successful architectures had many more free parameters than observations. So this would be like fitting a 10th order polynomial or spline when you have two observations. Nobody would think that's reasonable, right? But it worked very well on these image classification problems in practice. And then somebody started looking at this in the context of linear regression. So using, not just 2 points, but I'll give the setup in a bit more detail. And then what they observed is that beyond this point here, where my train error goes to 0, my test error starts to decrease again. This can be sharp or not, but the important thing is it can decrease. And now the stunning thing is, it can become lower than it ever was before. And then if it even reaches 0, then people call this grokking. Yeah, so to grok is to really understand something. Yeah, so in the modern regime, this would be the interpolation threshold here. And all right, and this is the very puzzling finding here. And this is what people call the double descent. Or some of the literature calls it benign overfitting. Benign is gutartig. All right, but now if we look at the blackboards on the left, apart from my wobbling of, why is this one term 0 here, this is very plain math, and this is somehow still right. So how can you reconcile it with the right-hand side? And well, the thing is, the bias goes down and it stays low, but apparently there's something funny happening with the variance. With the variance of your estimator, that as you give your model extra many degrees of freedom, this variance starts to decrease again. And this seems, and now why? I would say it's still an open research problem, but we will discuss, first steps towards explaining it. And one aspect at least seems to be, okay, I should write partly due to implicit bias that we use in our training procedures. So, for example, the fact that we use gradient descent or stochastic gradient descent, and importantly also how we initialize this gradient descent or stochastic gradient descent. All right, so this is just a phenomenon, and after the break we will start looking into explanations, and we continue at 10. I'd like to start with the correction from last time. You saw me puzzling on the blackboard. Last time we had this expression where this was the true underlying function. This here was noise, and that was the resulting label. And then we had some estimator, and we said that this noise has an expected value of, okay, there was one confusion. I had written a 0 with a small flourish, which some people read as sigma, okay? No, this is 0, yeah? So the expectation value of this noise is 0. And so what are the random variables? The noise is a random variable, but we also have this random variable of what training data we have. Yeah? So the data is this collection of training samples which is also a random variable. This follows a joint distribution. And then we had a term which looked something like this. This was, so we were looking at the expected mean squared error at some location x, and we had a term that looked like y hat minus f of x times epsilon. And this was taken with respect to the training data and with respect to the noise variable. And then I was asking myself last time, but this epsilon, it enters the true label, and the true label enters the data, so how can they be independent? Yeah? And then somebody gave the right answer. So somebody said it's about a new location or a new sample. You remember who said that? Somebody? Okay, anyway, that was the right idea. Yeah. So we are looking at the expected mean square error at some new location, and this is trained on historical data. So this y hat of x, this estimator here, this was trained on the data. This here anyway is a deterministic function. No random component here. And this is now the noise associated with some location x, where we're looking at the discrepancy between our estimator and the true label at some new location. Yeah? And this is the finesse in the argument, that D and E are independent. And that's the bit I didn't see last time. And if they're independent, then I can write this as the expectation with respect to the data. Only the first term at all depends on this data. And the second term refers to this noise variable. And then this part is 0, not sigma. This part is 0 as per our assumptions here. And that's why this cross term vanished, okay? Took me quite some time last night to to figure out the details of where did I make the mistake.